So, in the last lecture we were discussing the rate of deformation tensor. Okay. Gradient of the velocity, okay, which is Ex the rate of deformation tensor expressed with the unit vectors, and if I take this particular matrix alone of the gradients or the derivatives of the different components of the velocity, okay, I can of course express it in terms of the velocity components. Okay. However, there are some more fundamental components of this that turn out to be invariant, okay, under rotation of axis, for example. Okay. And therefore, I had in the last class taught you how to decompose these into a symmetric traceless part plus an antisymmetric part plus an isotropic part, okay, where I is the identity tensor. Okay. I has 1s along the diagonals and zeros along the off diagonal terms. Okay. And the antisymmetric part is equal to half of the tensor minus its transpose, and the symmetric traceless part is the symmetric part, which is half of the gradient plus its transpose minus the sum of the diagonal elements, okay, the sum of the diagonal elements. Okay. So, you subtract out 1/3 of the sum of the diagonal elements, 1/3 del dot V into I. Okay. And of course, you have the third, which is the isotropic part. Okay. And I had expressed in detail each one of these for you. Okay. So, the antisymmetric part has 0 diagonals and the off diagonals are negative of each other, okay, as shown over here. Okay. The symmetric traceless part, okay. So, basically you take the symmetric part and subtract out 1/3 times the identity tensor times the divergence of the velocity, and this is what I get for the symmetric traceless part. Okay. Now, what types of deformations do each of these represent? Okay. What type of deformations do each of these represent? Okay. I will discuss that for ease of visualization first in 2 dimensions, and then I will extend that to 3 dimensions. Okay. So, what types of deformation do each of these represent? Okay. So, in 2 dimensions, the gradient of the velocity can be written as okay, Ex Ey okay. So, that is what how it is written as. Okay. And once again, if I write it without the unit vectors, I just get partial Vx by partial x okay. The presence of the unit vectors is understood in this case. Okay. So, therefore, I can write this as okay, extensional strain plus antisymmetric plot plus in this case half, okay, del dot V times I, okay, where this E so okay, the first component is half del dot V I is equal to half divergence of V 0. Okay, so that is the first component. Okay. The second component, that is the extensional strain, is going to be equal to so that is the symmetric traceless part of the rate of deformation tensor. Okay. And the antisymmetric part finally is going to be equal to A is equal to 0, okay, half of so that is going to be the antisymmetric part. And let us look at the types of deformation that each of these represents. Okay. So the first one is, okay, half del dot V into I, okay, which is equal to and let us look at the relative velocity between 2 points, okay, in this 2 dimensional coordinate system, x y coordinate system, okay, in this 2 dimensional coordinate system, okay, at different locations which are separated from by equal distance from the origin. Okay. Okay. So, if I go a small distance, okay, so basically I had told you that the gradient of the velocity tells you, if you go a small distance delta x in any direction, what is the difference in the velocity between 2 locations at x and x plus delta x. Okay. The location x in this case I will fix at the origin, and x plus delta x I will fix at equal distances in different orientations in the xy plane. Okay. And I will ask what is the difference in velocity between these 2 locations because of this kind of deformation, okay, because the deformation of this kind. Okay. So, therefore, I will get delta V is equal to delta x dotted with grad V. Okay. And for this deformation in which grad V is equal to, okay, so this will be delta x dotted with half del dot V 0 0 half del dot V. Okay. Okay, so that is the matrix. Okay. Note that the first index in this represents the direction of the gradient. Okay. In this, the first index is the direction of the gradient and the second is the direction of the velocity. Okay. So, what is it for a deformation of this kind, okay, of this isotropic deformation? Okay. I can write the difference in velocity, okay, delta Vx delta Vy, okay, is going to be this. Okay. So, this is going to be delta x and delta y. Okay. This is delta x vector, okay, delta x and delta y dotted with half I del dot V 0 0, sorry, there is no I here, the diagonal elements are the divergence of the velocity, the off diagonal elements are 0. Okay. So, this is what I get when I multiply the gradient of the velocity with the dot product of the separation times the gradient of the velocity, the difference in velocity between these two components. Okay. So, therefore, I will get delta V x is equal to half del dot V delta x and delta V y is equal to half del dot V times delta y. Okay. So, at a location x plus delta x, okay, at a location delta x, the velocity V x is proportional to delta x and the velocity V y is equal to 0. Okay. Similarly, if I go an equal distance minus delta x, okay, so if I go a distance plus delta x, I get the velocity in this direction. If I go distance minus delta x along the x axis, the velocity is in the minus x direction. V y velocity is 0 in this case. Similarly, if I go a distance delta y, same distance, okay, the velocity is in this direction, okay, because V y is equal to half delta y times half del dot V. Okay. And if I go in the minus direction, I get a velocity in this direction. Similarly, if I go in different directions, I get a velocity that is radially outward. Okay. Okay. So, therefore, this isotropic part of the rate of deformation tensor, okay, this isotropic part of the rate of deformation tensor, it represents radial expansion or compression. Okay. It represents radial expansion or compression. Okay. Similarly, in 3 dimensions, okay, in 3 dimensions this same will represent radial expansion or compression from a spherical surface, okay, radial expansion or compression from a spherical surface in 3 dimensions. Okay. Okay. So, that is the isotropic part of the rate of deformation tensor, okay, which is proportional to the divergence of the velocity here. Okay. This isotropic part is proportional to the divergence of the velocity here. Okay. And this, there can be isotropic expansion or compression, that is change in volume. Okay. Note that mass has to be conserved, total mass has to be conserved. So, there can be change in volume only if there is a change in density, okay, only if there is a change in density. Okay. Recall, we had written the mass conservation equation as partial rho by partial t plus divergence of rho times the velocity is equal to 0. Okay, this was the mass conservation. Okay. Alternatively, we had written as partial rho by partial t plus v dot grad rho plus rho del dot v is equal to 0. Okay. And these two terms, if you recall, these two are the substantial derivative. Okay. In a reference frame moving with the fluid velocity, d rho by dt plus rho del dot v is equal to 0. Okay. So, that is the mass conservation equation. Okay. This implies that the rate of change of mass, okay, the divergence of the velocity is equal to minus 1 by rho d rho by dt. Okay. Therefore, if the divergence is positive, that means the density is decreasing, okay, in the differential volume. Okay. Physically, that makes sense. If the divergence is positive, there is volume that is expanding. Therefore, the density has to decrease because the mass is a constant. If the divergence is negative, there is compression. Therefore, the density has to increase because mass is a constant, volume is decreasing. So, this basically represents volumetric compression or expansion, and this is related to the symmetric, the isotropic part of the rate of deformation tensor. Okay. So, that is the kind of deformation that is represented by the isotropic part of the rate of deformation tensor, okay, radial expansion or compression. In the case of incompressible fluids, there is no radial expansion or compression. Therefore, the isotropic part has to be 0 or the divergence of the velocity has to be 0 in the case of incompressible fluids. In the case of compressible fluids, the divergence of the velocity is related to the rate of change of the density. Okay. So, that is the first component. Okay. That is the first component. Okay. And this holds whether it is in 2 dimensions or 3 dimensions. Okay. So, this is the first component of the rate of deformation tensor. Let us look at the second component, that is the antisymmetric part. Okay. In this case, I can write the rate of deformation tensor as in 2 dimension 0, okay, a times minus a and 0. Okay. Okay. So, using the same relationship, okay, delta V x delta V y is equal to delta x delta y into 0 a minus a 0. I can write this as delta V x is equal to delta V x is equal to this times this minus a delta y, and delta V y is equal to a delta x. Okay. So, that is what I get when I do the matrix multiplication. Okay. So, once again let us take our coordinate system. Okay. The origin, and I go a distance delta x delta y around the origin, okay, in different directions. If I go a distance delta x in the x direction, okay, so let me put the coordinates here x and y. Okay. If I go a small distance delta x, then you can see that delta V x is equal to 0 and delta V y is equal to a times delta x. Okay. That means that delta V y is in this direction. Okay. Similarly, if I go minus delta x direction, okay, you can see that delta V x is 0 because delta y is equal to 0. Delta V y is equal to a times delta x. In this case, delta x is negative. Okay. Therefore, this is the velocity here. Okay. If I go a small distance delta y in the y direction along the y axis, delta V x is equal to minus a times delta y. Okay. So, delta V x is in this direction. Okay. And if I go a small distance delta y in the minus y direction, then delta V x is equal to is positive because it is minus a times delta y is negative. Okay. So, therefore, I get a velocity that looks like this. Okay. And you can go in other directions, and on this circle where the displacement is equal, you will find that the flow looks like this. It is a rotational flow. Okay. This is a solid body rotation about the axis. Okay. So, the antisymmetric part of the rate of deformation tensor represents solid body rotation. Okay. And this antisymmetric part can be related to what is called the vorticity. Okay. We had briefly discussed that when we did vectors and tensors. The vorticity is equal to the curl of the velocity. Okay. Vorticity is equal to the curl of the velocity. How do we calculate that? Okay. We calculate that by taking the determinant of this matrix Okay. So, this is equal to E x into partial V z by partial y minus partial V y by partial z, E y into partial V x by partial z minus partial V z by partial x, okay, plus E z into that is the curl of the velocity. and therefore, this vorticity has components omega x is equal to partial V z by partial y minus partial V y by partial z. Omega y is equal to partial V x by partial z minus partial V z by partial x. Omega z is equal to partial V y by partial x minus partial V x by partial y. Okay. That is the curl of the velocity. Okay. Recall when I had written the antisymmetric part of the rate of a deformation tensor. Okay. Okay. I had written the antisymmetric part of the rate of deformation tensor as, okay, so let me write it here. Zero partial V y by partial x minus partial V x by partial y, okay, and partial V z by partial x. Okay. I have to have a half outside. Okay. Okay. And each of these terms can now be identified with the components of the vorticity here. Okay. You can just identify these with the components of the vorticity. Okay. So, this first term is 0, partial V y by partial x minus partial V x by partial y. Okay. So, half of that. Okay. So, this is just going to be equal to half of omega z. Okay. Partial V z by partial x minus partial V x by partial z. Okay. Partial V z by partial x minus partial V. So, this is minus half omega y. Okay. This term is partial V x by partial y minus partial V y by partial x. Okay. And this is equal to basically minus half omega z 0. Okay. And this term is partial V z by partial y minus partial V y by partial z, which is half omega x. Okay. This is half omega y minus half omega x 0. Okay. So, the three independent parts of this antisymmetric part of the rate of deformation tensor are all related to the components of the vorticity. Okay. Okay, these are all related to the components of the vorticity. Okay, so, okay, these are all related to the components of the vorticity. Okay. Okay. So, I can write this also as the relative velocity. Okay. You can also write the relative velocity as delta V is equal to half omega cross delta x. Okay. So, what let us look at what this half omega cross delta x gives you. Okay. Okay. It's equal to half is equal to half Ex into So, this is the same as what you get by writing this delta V is equal to So, rather than the antisymmetric part of the rate of deformation tensor, if I use this same antisymmetric part expressed in terms of the vorticity, if I use the same antisymmetric part represented in terms of the vorticity, and I write delta x, delta y, delta z times this, you can see that you get the same expression as this one. You get the same expression as this one. Here I will have Ex, Ey, Ez for the components of the velocity. Therefore, if I have a velocity difference delta V is equal to delta x cross half omega. Sorry, it is the other way around, I should write. Note that if you have a solid body rotation, if you have an object that is rotating as a solid body with some angular velocity omega, if you have an object that is rotating with as a solid body with some angular velocity omega about the origin, and this is delta x is the difference, is the distance from the origin, the linear velocity at this point delta V is going to be equal to omega cross delta x. The linear velocity at this point is going to be equal to omega cross delta x. Therefore, this delta V, which is half of omega cross delta x, basically represents solid body rotation with angular velocity omega is equal to half omega. So, the antisymmetric part of the rate of deformation tensor represents solid body rotation in which the angular velocity is equal to 1/2 of the vorticity at that location. So, it represents a rotational flow in which the angular velocity is equal to 1/2 of the vorticity at that particular location. So, in my initial expression, I had separated out the rate of deformation tensor into 3 parts. The symmetric traceless, the isotropic, symmetric traceless and antisymmetric. And I had shown you isotropic part represents the volumetric expansion or compression, and this involves a change in density. For an incompressible flow, this component is equal to 0. Antisymmetric part represents solid body rotation. The components of the antisymmetric part of the rate of deformation tensor are related to the components of the vorticity, which is the curl of the velocity, and it represents solid body rotation in which the angular velocity is equal to 1/2 of the vorticity. The angular velocity vector is equal to 1/2 of the vorticity. Next is the symmetric traceless part. That part I will continue in the next lecture. So, I will continue this lecture then, and we will see you then.